Lo ponemos. Okay. Okay, I think we can start already. So thank you very much for being here. Today the seminar is going to be given by Eduardo Suelves, which is our visitor for mid-August.
Yes.
So he's from Huesca. He's an Aborigine. He studied in Zaragoza, and then he moved to Bonn for the master, and now he just finished his PhD in Warsaw. So the talk today is about the sky background features on galaxy mergers. All yours.
Thank you very much, Juan. So yeah, welcome to a preparation of my PhD defense. I will basically show the results of my PhD that I submitted not yesterday, but the previous Monday. So this is going to be the outline. The main thing is going to be based on a paper that we published at the beginning of last year. So I will begin with an introduction, giving context, of course, to galaxy mergers and galaxies. Then the main finding that we made in this work that was related to the sky background error, and then a couple of extensions that we try to do with the methodology that we learned in that publication, and of course, the conclusion afterwards. And with this, I will begin with the introduction. And of course, talking about galaxy mergers, I need to start with some panels of how a galaxy merger looks. Galaxy mergers are the interaction between galaxies, and because of the tidal forces between the two galaxies as they approach to each other, then the galaxies get distorted, and then these tidal forces then start creating tidal tails, arms, and reaches between them. And of course, as they start approaching to each other, the interaction becomes even stronger and they get even more distorted. And if the relative velocity is not too high, they will end up approaching to each other subsequently until they finally become one final galaxy. And the reason why we wanted to study galaxy mergers are actually many, because they seem to be one of the main drivers of galactic evolution. Here are a small list of reasons why we care about galaxy mergers, that they are important in the transformation between early and late type galaxies. They seem to be related to many of the quenching and star formation processes in the universe. Also, because galaxy mergers are two galaxies merging with each other, becoming one, they are related to the growth of structure in the universe. They also give us an idea of the time scales of galactic evolution. And last but not least, is actually what is going to happen with the Milky Way and the galaxy of Andromeda in the future. But before going on a bit more about work with galaxy mergers, let's actually go a bit more in detail of what is the relation of galaxy mergers and galaxy evolution. So, of course, we all know the typical type of galaxies that we have in the sky, right? We have elliptical, basically ellipsoids of stars. And then we have spiral galaxies, like the Milky Way, with the central bulge and more bright part. Some of them with a bar crossing the bulge in the middle. Of course, the spiral arms. And something that we have in between that are the lenticular galaxies that look something right between elliptical and spirals, with a bright center but also some disk around. And this was one of the first things that were discovered when the study of galaxies began. And this is basically one of the first diagrams of type of galaxies that we have, right, from Hubble in the 1920s, in which we had this famous Hubble tuning fork that basically would collect elliptical galaxies with some evolution related to the two types of spiral galaxies with the lenticular symmetry. Okay, so then we have two main types of galaxies that are elliptical and spiral, so that they are the more common types, but let's put in quotes. Let's put that in quotes. Then the ellipticals generally are populated with all stars. Because of that, they are redder, and then they don't have as much gas and not that much star formation, and overall they are massive and redder than spirals. But also, we have that the spirals have young and old stars, so they have a combination, right? Like we have the redder part in the center, but also the bluer part on the arms and on the disk. Then Because of that, they have more gas, they keep forming new stars, and then overall they are less massive and bluer. So, of course, galaxy evolution is a very difficult research, but we have some channels in which we know that galaxies may have reached to these points. So let's try to figure out why they are so different. So we know that in the result from mergers can actually produce transformations between galaxies. So we were saying before, transformation between early type galaxies that are elliptical and late type galaxies that are spiral. So we know that it's very likely that major mergers, so two galaxies that are of similar size and that are in this case spiral galaxies, when they merge, at the end they produce a bigger elliptical galaxy. So basically what is happening is that two massive spirals of similar mass merge into an elliptical galaxy. So basically the process is consuming the gas of the original two spirals, becoming a bigger but then quenched elliptical galaxy. But we also have the second channel that would be, we have a spiral galaxy, then it has a minor merger, so a small galaxy entering into the bigger galaxy, like a satellite in foreign, and then this produces an enhanced spiral. So basically it's like the spiral galaxy is feeding from small galaxies. And actually we know that this is one of the things that has happened to the Milky Way, because we know on its merging history, there is 6 confirmed minor mergers or satellites that have been falling in the Milky Way and that we have been able to trace nowadays. And yeah, this is some of the channels, two of the main channels we know well nowadays. But of course, we have a full slew of galaxies. There is a huge amount of different type of galaxies. It depends on the moment of the process, of the life process that we find them, also of the cosmic time in which they are located, how far they are, and everything. So of course, there is a lot to discover. And because of that, we want to find, all the galaxies want to find galaxy mergers. We want to discover how galaxy evolution works, and because of that, we want to find it. And we can do it in many ways. We can do merger identification. So the first one would be visual inspection. So we have professionals that just have images of galaxies, that the one that we're looking at before, and then we say, okay, this is a galaxy merger or this is. Very simple, time-consuming, definitely tiring. Other thing that we could do is the closed pairs methodology. So we can find galaxies in the sky that are next to each other, so we can find pale sky neighbors, and then we estimate the radial distance, right? We calculate how far they are out from the redshift, and then can tell if they are merged. Here we would have an example of two galaxies that are basically close to each other in the sky, but they are not interacting with each other. More sophisticated way would be to do a morphological analysis. So we calculate parameters from the images that are quantifying the shape distortions of the galaxies. And because nowadays we live in the high computing era, right? We have many different types of models that are accelerating every process that we can do with data. We can apply machine learning. We can apply convolutional neural networks that are models that are properties that are going to that characterize these galaxy mergers, and they do that from the images. All right. So then, talking a bit more about machine learning and convolutional neural networks, these type of models, what they are is supervised machine learning. So they get input raw data, and then because we know the labels, we know the type of sources that we have in the input raw data, like the type of fruits that we have, then at the end in the output, our model, our supervised learning model, would actually learn the properties, right? We identify the different type of labels. For this, we need two things. One is the training data set, and of course, the model type and structure that we would like to have. But in my case, what I did in my work was to apply machine learning, but actually not a convolutional neural network, but just a neural network. Our idea was to try to use only photometry to find galaxy mergers. The main goals for doing this were two. Of course, saving time and resources, because if instead of using images, we just use parameters on a table, it will be much easier. And also because we might learn some new properties. And if this is not enough for catching your attention, here, of course, you have seen a very huge bison in the middle of the screen. This is because it's actually one of the most famous animals in Poland. There is this forest in the east side of the country that are full of bisons. They actually have cameras online that point at different parts of the forest. So yeah, if the science is not interesting enough, remember the bisons. And of course, this is, as I said at the beginning, the first part of the work, and the extensions later on are based on this paper published at the beginning of last year. All right. So then with this finished introduction, and then I will explain what I did. So of course we were applying some machine learning and we were applying some supervised learning to find galaxy mergers. So we needed some labels. For that we used Galaxy Zoo. It is a citizen science project for visual classification of galaxies. So a web page that you can just enter and then classify some galaxies and give your opinion on what they look like. This is how the interface looked for the first data release. So around 15, 16 years ago, I think, or even more. And yeah, so the main output that we care about from this Galaxy Zoo for our project was the merger both fractions. So how many of the volunteers that observed galaxies decided that, hey, this looks like a merger. So then we made a selection of the training data set. So we got mergers that were actually not directly from Galaxy Zoo, were from this paper, like I told 2010, in which they confirmed high, galaxies that had a high both merger fraction, this high FM data. So then from these mergers, we got also non-mergers. Those are directly from Galaxy Zoo with those galaxies that have a low both fraction FM. And then we built a class balance dataset. So we wanted to have the same amount of mergers and the same amount of non-mergers in our dataset. So we got 2,600 mergers, 2,600 non-mergers from training, a 10% of that for test. We got in this time range, so 0.01 to 0.01. I haven't said, sorry, but all of them were from SDSS. And also, because of course there were more non-mergers than mergers, we made a nearest neighbor match between R magnitude and spec C. So we wanted to have mergers and non-mergers that were similar statistically. So then we used like the R magnitude as a proxy of the mass and the spec C as a proxy of the distance. All right, and then because we have a neural network that wants to use only photometry, I need to talk about the inputs. So the input information were mainly two. And we used magnitude, colors, and errors, and we used two types of flux calculation methods. We used model calculation method. We use model fluxes. We use model magnitude that in SDSS is the fit of a luminosity profile to the surface brightness profile to the galaxy, and then an aperture flux that is nothing more than an aperture around the source. And as I said, the magnitude, the colors, and the errors for each of them. And we did this for the 5 optical bands of SDSS that we have here, U, G, R, I, and C. And then we use a neural network. For those that might be not very familiar with neural networks, this is a mathematical model, right? In which we have some inputs, then some hidden layers that are mathematical connections that are moving the information from the input to the output. And then these internal layers are where we trained the parameters. This is basically where the model learns, and then it goes to the output. The output in our case is a binary classification, so labels of mergers and of non-mergers. And yeah, we got the input, the photometric parameters, then during training, the hidden layers get their own parameters in order to make the output layers the closer to the initial labels as we want. Okay, and then with this, we can start talking about the results that we got. So first of all, we made a k-fold cross validation. So we separated the training in 5 groups, and then we trained we did this so that 4 of those groups were training and the last one was a validation, in order to then create 5 trainings. And these 5 trainings are the reason why we have in the accuracy we have errors. And then in this plot, I want to show you from bottom to the top. Okay, so in here I have the accuracy of the validation set, and then beginning we have these fiber magnitudes that are the aperture magnitudes that I talked about before. So we trained a neural network on those, and then we obtained a 60% of accuracy. Then we did the same, but with the model magnitudes, which, as we could expect, because the model magnitudes are closer to the profile of the observed galaxies than the simple aperture magnitudes, they are slightly higher. So instead of a 60%, a 65%. Then using the colors that are nothing more than the subtraction of the different magnitudes, we got something very similar, which makes sense. And interestingly enough, when we combine both of them, the model magnitudes and the model colors, we got something slightly higher. which we interpret as the neural network having more information and then being able to extract a bit better the information, the knowledge of the data. When we added the, I think that's mine. No, wait, I don't know what that is. Where is that? Okay, I know. This was silence. Sorry. So then, okay, so I will go back. So the magnitude and colors, and then combining the errors, adding this to this data set, the errors, we got something slightly higher and a bit more stable with less error. But what was very interesting was that when we swapped that with the fiber, we swapped this with the fiber magnitudes, with the aperture magnitudes, colors and errors, we got something much higher. This was definitely very surprising. And in fact, if we got only these fiber errors, we got something much higher than any other photometric parameter. So we got this around 83%. So we were very, very curious about what was happening here, and then we tried to figure out how these fiber magnitude and fiber errors were calculated. So the fiber magnitudes, they come, as I said, from aperture magnitudes around galaxies. They actually have the size of the SDSS fibers, because SDSS is an spectrometric survey in which this is how they used to do in the database I am working with. They had the plates and they could input the fibers in order to get the spectroscopy, right? And so the aperture magnitude is not the aperture, is not exactly what the fibers is, but it's actually kind of adapting from the image, getting what the magnitude that the fiber would see, right? So as you see, like an aperture of 3 arcseconds of diameter. And then the error depended on 4 parameters. One was the counts within the aperture, so the ADU that were within the aperture. Then other were the dark current variance, so they were parameters related to the camera only, and then the sky background and the sky background error. And then we started to combine things to the neural network, because at the end of the neural network, we can say that it's simply a black box where you input some numbers and then it gives you some results at the end. So we said, okay, we have these 4 parameters, 5 magnitudes, so 20 numbers as an input. So all the inputs, and we got something fairly high, 91% or so. And then we started combining things. So then we combine, for example, the counts within the aperture, then the sky level, and the dark variance. And we got something very low. And then, of course, this meant that this was the sky background error that had information, and we started combining it with things. So then the fiber counts and the sky background error gave something very high. And interestingly enough, the sky background error with the dark variance, that depends only on the CCD, or depends only on the camera, was also very high. And then the sky background error alone gave an 83%, that was the same thing as the fiber errors gave. Okay, so what is happening here? What was happening was that it depended on the normalization. And all these parameters, they are min-max normalized. So that means that all the numbers that were given to the neural network were normalized between 0 and 1 for each galaxy. When I took out, and that was the reason why the sky background error with the dark variance was so high, because then when they were normalized together, the numbers of the sky background error were shown in a different way to the neural network. And we discovered that using the logarithm of this sky background error, we got something very high. And it was actually the best neural network that we obtained. For the validation, we got around a 92.6% of accuracy, and for test, a 92.3%. So also showing that it is not just some overfitting that we obtained from the model. And then, okay, we decided to try to understand why this strange parameter was doing things so well. So then we're starting to try to observe the feature space. So these panels are, of course, histograms with the number of galaxies, of the sky background error, the sky error in the 5 SDSS bands, and the first row is the true positive. So the mergers that were correctly identified by the neural network. The third row is the true negative, so the non-mergers correctly identified, and then the cross cases. And I want you to look at these 9 panels in the center. So if we look at the true positives as to all the mergers correctly identified, they are clearly in the higher part of the histogram for these 3 bands. And the non-mergers are in the lower part. And in fact, the false negatives, which are the mergers that were identified wrongly by the neural network, they are also in the lower part. Which means that the sky background error is high for mergers and low for non-mergers, or for a fairly big amount of all of them. And this actually gave us the idea, okay, maybe we can, instead of just like using our neural network, maybe we can decide to plot this on a parameter space. And this is what we did. We made this plot here, in which in in the x-axis we have the G band of the sky background error, and in the y-axis the R. And then we plot the mergers and non-mergers. Mergers are these orange crosses, and the non-mergers are these blue crosses. And then we draw a line between them. And we got a 91.6% accuracy. So only 1% less than the neural net. It looks very good, like all the mergers are in this side, but of course the non-mergers are plotted on top. There is some non-mergers here. Some mergers located in here would correspond to actually this part here. Okay, so we found a very good way to find mergers, and we also had an interpretation, a physical interpretation of why this might be happening. So what we think is that the sky error is tracing low signal to noise structures. So if we look at this galaxy, it's having some small tidal disruptions, like this tail here and this part here very distorted, and kind of like a part here looks like a satellite that is moving around. So what we think is that the sky background error is able to trace this in the images. But of course we would like to prove this, and also one important note is that the catalog from where we took the galaxy mergers from this catalogue 2010 has mainly merging major pairs. So basically two galaxies that are similar size merging with each other. So of course it would be interesting to see if we could find this in other stages and type of galaxy mergers. And this was the first work, and this was what we published. And of course we wanted to try to learn more things of this project, so we tried to extend it. The first iteration that we made was for more galaxies in SDSS. We took literally all the galaxies that are in the same galaxy data release as our training dataset, and we located them in the parameter space that we have the decision mountain. So all the SDSS DR6 data are these green dots in the background behind the training dataset. And well, we had like around 300,000 galaxies, and so we had a lot. And just by the line cutting the diagram in the middle, we got around a merger rate of 13%, which is higher than what we generally see, which might mean that something is happening. We, for example, decided to, okay, maybe it's not only the boundary, but maybe there is an area where that mergers are mainly located. So we tried to narrow down kind of like an area where mergers would be mainly there. And then we found actually something a bit more sensible, 8.6% of accuracy. So then we were like, okay, maybe that's where we should look for galaxy mergers, at least in this parameter, in this data release. But of course, there is some problems when trying to find galaxy mergers, and one of them is contamination. And in order to explain it, I'm showing, of course, a very famous image that is the Stefan quintet. This is the image from the James Webb, in which we have 5 galaxies merging with each other. Sorry, 4, because it's 1, 2 that are clearly interacting already, and 1 that is still approaching, and then a 5th galaxy that is actually next to them, but is in a different plane. It's not really interacting. And this is galaxies that we have very high resolution. We have very good detail on them. We know exactly what is the redshift. But if we go to the background images, for example, well, here in this corner, that they are much less resolved, getting specs from them is not so easy. We can get galaxies that, for example, this one in here, that is clearly very distorted, and might be interacting with this one here, very small. I don't know if you really can see it. But also there is other galaxies nearby, right? Very close, this one here, or this that look to be, because they are much redder, look to be not in the same area, right? So we might be having problems on contamination in this diagram. And in order to show this, I'm going to actually show how galaxies look like along the diagram. So we're going to go with the bottom. In the bottom part is here, that this is actually where some majority of the false positives were located. We have this galaxy here that is interacting with this one here. Not very high resolution, as you can probably see, and doesn't seem to have it seems to have some like low signal to noise around, but still maybe not kind of like as spread as all the images that we were looking at before. If we now go to the middle, we have something a bit brighter, and maybe with more spread distortion around the image. We have around, so this. Of course, the resolution is not the best, but we could tell that these galaxies might be interacting. But then if we go to the higher part of the diagram, what we have is mainly galaxies with a very bright star around. So this was telling us that in order to use the diagram, we might need to take care of some contaminations. And in fact, here we mainly have stars, galaxies with a star. Okay. So then, we try to observe different areas of this diagram. So this is might look a bit complicated, but overall we have this part that is mainly the mergers, again in orange as before, and then we try to look around. We made like a rectangle, and let's see what we see, and do some statistics around the rectangle. So this bright part here, then two wings on the side, and something that connects with the diagram in the middle, and then two parts of non-mergers. It was looking at the diagram, it was basically where the non-mergers seem to be mainly located. And we have them plotted like this. And then what we did was to look at galaxies, to visually inspect galaxies in different positions there, and see how they look like. And this is the diagram that I have later. So the first row, this is all the galaxies that we saw some contamination. It could be either stars next to the galaxy, or maybe some visual pairs, or some galaxy that is next to the target galaxy, but is not really interacting. And this would be the clean case. So galaxies that are just without anything next to them. So if we start from the bottom in the clean case, then the columns, these are major mergers, so major merging pairs, then other type of mergers, so minor mergers, satellites foreign, maybe covalence cases, and then of course non-mergers. Then the major mergers are mainly located around the area of where we thought the mergers are. Also, the distribution is a bit misleading because I think this is important to say, because the selection was just not a flat selection of the areas. There was a lot of like minor selections and so on, so it might look a bit complicated. But I think the message is still goes with the plots. You can tell me at the end. So yeah, mainly major mergers there, but of course everywhere. Then the other type of mergers seem to be kind of like not so high, like maybe more next to the boundary. So maybe it would be finding other type of mergers would be useful to modify a bit the parameter. And the clean non-mergers were mainly located also lower. So mainly in this part, the lowest sky background error possible, and in this part here. But of course, then we have the dirty case. And the dirty case, the most important thing is here. We have non-mergers with stars nearby, galaxies nearby, all around the parameter space. So it would be very nice if we want to get catalogs of mergers using this parameter to be able to get rid of this contamination, to get rid of these distortions. For this, we made a decision tree, very simple one. So we said, okay, we are going to consider dirty galaxies if they have, so dirty targets if they have, and a star that is closer to the target source to 2 times the Petrosian radius, and then if they have a galaxy closer to it, that is if a nearby galaxy that is closer than the Petrosian radius of the target and the Petrosian radius of the other one. These numbers were basically, by the visual inspection, right? We decided that this is okay. This is when they look dirty and when they seem to have a higher sky error because of the presence. This was consistently what we used to find. But then we would consider them clean if there was a cross pair. So if there was only one galaxy nearby, and also if this galaxy nearby was a cross pair, or if of course there was no other nearby source. So then we applied the decision tree to the data sets that we have here. So now something to begin with, and then we actually got something fairly decent. So first of all, it discarded 67% of the contaminating non-mergers, and it kept 72% of the clean mergers out of this data set. So this was the main result out of this first stage. But then we had another question at the same time that was, okay, could we actually extend this to deeper data? So not use only SDSS, but maybe use some other survey. So then this is what we did. We extended it to deeper imaging and the Subaru Hyper Super Income dataset. And because of this, and because we think that the sky background error is tracing low surface brightness features, we said, okay, HSC doesn't have the same background error parameter that we have in SDSS. So maybe we can try to do it ourselves. So then with some galaxy mergers and non-mergers that we have in there, we made, okay, we're going to get an aperture around the galaxies, we're going to get all the pixels around them, we're going to get the background within the aperture, and then we're going to mask everything that is above the 1 sigma of the background, which is basically what we have masked in here. And then we are going to get a histogram of the low surface brightness or low signal to noise pixels of the aperture. And we're going to do this also the non-radius, which is also it's easier to see, right? We have some fairly not to resolve galaxy, so we can get just the background around. But there was also one very important thing that is okay. The images that we were working with, they are reduced, so they have the background subtracted from them. And in fact, when we were trying to reproduce the sky background error, this parameter on the images of SDSS, it did not work because the background was already subtracted. And for the data that we are working, data release 6, you cannot put the background back. You can do it for data releases, but not for this one. And then, okay, we actually had a catalog of mergers in the HSC North Ecliptic Pole, in the deep field there, and also access to some of the last galaxy subclassifications, also in that deep field. And we were like, okay, observations in this deep field are actually, they are actually, like the raw images are public. So we can actually maybe reduce them and see if we can try to find some parameter taking into account what is the effect of the background. Okay. So I hope you are prepared now, because now we're going to talk about the pipeline of HSC. I hope you have a lot of patience. But I'm going to try to be very fast. I'm going to try to focus only on where the background was calculated, okay? Because, okay, so we have the raw data, good, you get it from their not survey, from the server. So then the pipeline subtract the bias, the dark, apply the flats, and so on. Then, and it does all of this per CCD. Then, of course, it has some source detection, and this is where the first background subtraction is done. So, in order to get the sources in the image CCD, it subtracts 3 subsequent sky backgrounds. It does it while it does the detection of the sources and the calculation of the PSF. So, okay, we have all of this applied on each CCD, and we have raw CCDs from the camera with these 3 subtractions, and then because we have a deep field, they are going to coat images, right? So then, of course, we have an astrometry, and then we coat the images to get deeper images. And it is in the coat where there is 2 extra backgrounds. Interestingly enough, before doing those backgrounds, then they are added back, the ones of before. So we consider that because these backgrounds during detection are added back during the coat, we are going to consider them to not be affecting the background in the image. And then there is 2 backgrounds in the focal plane, so the whole camera, and one of them comes from dithering. So the idea was to, okay, the other background is a background that is very, very like large scale, so in principle it shouldn't be affecting the small sources that we have, but maybe the one on the made out of the dithering might have some effect. So this is the one that we decided to discard. So as I said, the 3 backgrounds from the source detection, we just consider them they are not going to give any problem, and then out of the others we just cancel the other one. And this image is this is the fit files, this is the HDUs of the images. It might be a bit confusing because this is, for example, the image of one of the background, and this is the variance, and this is the mask, and this is done 3 times. So yeah, this is the initial background, right? The one created during the source detection. Then this is this first global background, the one that is just on the focal plane with large structure, and then the one from dithering, and then the variance and the mask. So what we did was these 3, let's set them to 0. And that's it. Which now sounds very simple, but it took a while to figure out how the pipeline worked and talking with the helpers from the HSC software and so on. But in principle, with this dithering was not applied anymore. And now I'm going to show you what were the results. So this is a code of so this doesn't look like anymore like the CCDs that we had before. This is a proper code. And this is the one that we calibrated with the sky, and then this is the one that we calibrated without the sky, where we set the dithering to 0. And this is the difference. So if you see, for example, this part that has many bright stars, when the dithering is not subtracted, when it's not applied, you can see that there is this halo of bright, this brightness halo around the bright stars is still there, but is well subtracted during these other days. And there is also, for example, this part in here where this, like some, not over subtraction, but it's like this is not corrected well there, and this is what you can see here. Like this is the difference. So this gray part, that means that this one is higher. So you can see he is higher, more signal in this part, and then the other around. So okay, it seems that we are able to trace what is the dithering background is doing. But if we now go to what we actually care, that are smaller sources, they are fairly similar. So first of all, if we look at the cutouts, you can barely see very like difference in the axis and so on. And when we look at the actual subtraction, we do see some structures. We see kind of like some noise and then some flat parts, but they don't seem to trace quite strongly the shape. A bit, but not too much. And this then goes to the results that we applied to the sorry, I should have made these slides there. So because now, okay, we had all these images, we have all this abstraction, and then we applied some parameters to these histograms. And we try to separate the mergers and non-mergers using those histograms. And this is the different parameters that we made. So to guide you a bit, this is the mean, this is the median of the low signal to noise histogram, and then we also apply the skewness, the kurtosis, the interquartile range, and some parameters depending on quartiles, and this is what we got with the normal scale. And then when we cancel the dithering background, we got something very similar. Of course, this is just by eye. We would need to like properly check the distribution of the parameters, but overall we can say that the difference on the background is making something big. And then all of this leads to the final goal of this work, that is to try to parameterize to find galaxy mergers in HSC. So then we combine all these different set of parameters that I showed before, then we apply some dimensionality reductions, and then we try to find, similarly to the first diagram, a region occupied by mergers. And this is another preliminary result. This is applying NCA to the 8 parameters, and this is to the normal scale, so no background subtraction, everything is normal there. And then we see that, of course, the majority of the sources are fairly close to each other, but still we got some area that it looks to have more mergers than non-mergers. And in fact, well, there is around 50 mergers, 30 non-mergers, 62% of accuracy. And the goal is to basically do this bigger, right? Have more data and more parameterization, trying to understand how the low signal to noise pixels look. And with this, I will go to the conclusions. First of all, the future work, that would be this decision tree that I talked before, trying to work with the contamination, doing some small redesign, and then optimize the parameters for finding the contamination. Then in HSC North Ecliptic Pole, run all the bands, because this was only with the G band, and of course the parameters was the G and the R one. And also it would be good to include some more parameters on the low signal to noise pixels. And then the deeper goal, the final goal would be to extend this to deeper images, like for example SST. I just put the long acronym for the other day. And then another thing would be, that is actually what is being almost finished now by a colleague in Krakow, in Poland, that it would be to apply a CNN on the galaxy residuals. Because if the sky background error is tracing like low signal to noise around the galaxies, that basically is the residuals that are around the source. So he's working on a CNN there, finding promising results, and this is my summary. So of course mind the errors, because that's sometimes they can be very useful, and is where the physics are. And then that we apply this neural network that help us to figure out the sky error parameter, and then we made some extension of the decision tree and the deeper imaging that are in very good process and close to finishing in the next months. And with this, thank you very much. I hope it was not very dense in the end, and I hope you liked it also.
Thank you very much for the very nice talk. Now questions, Andre?
Thank you, Luis. Very nice talk and very interesting work as well. I have a question regarding the selection of mergers in the SLOAM digital sky survey. So you mentioned that you are basically you're using the sky subtraction error that the pipelines provide.
Yes.
But the angular size of the object that they are pointing to with that fiber surely has to have an impact on this sky subtraction. And if I remember correctly, you're just doing a selection in redshift from 0.0 whatever to.
Yeah.
Are you have you considered studying also the impact that has, for example, the stellar masses of the system, so, or something that is equivalent, like the, I don't know, the radius of the system or whatever. So how those things would impact the position in this diagram?
Yeah.
And also the other question that I have is that you're using a selection that is based on Galaxy Zoo, and then you mentioned another paper?
So it was a paper that the results from Galaxy Zoo that had high votes, then they further classified them and then confirmed if they were mergers or not.
Right. So I was wondering whether those papers had some bias in the selection regarding signal to noise, for example, in the sense that, for example, Galaxy Zoo, these are very bright things, right? So whether you could export that to the main sample, or you had to do some selection or something like that.
Yeah. Well, actually, I think I was noticing what I was saying it, and just looking at the numbers, because so in this, so sorry, yeah. So this selection, those are actually the ones that are in the same redshift and magnitude interval as the dataset, but yeah, like totally is super related to the magnitude size. So one of the reasons why I was saying, I forgot there were so many slides in it. So I was saying that this is not representative is because for visual inspection, I made magnitude selections. It was kind of like the closest proxy I could think of for doing it fast. And like, there is definitely a dependence, like the brightest sources. Of course, if they are too bright, then I don't know how much trustworthy they could be. But if they are too low, they totally tend to be like in this part also. There is no much option. So it definitely has a high dependence of the resolution. Total.
And could you like, I don't know, like create, instead of using just 2 dimension, try to see whether there is another extra dimension in which you can further separate the 2 populations?
Yeah. So I haven't tried that. Yeah, but yeah, that's like that would be really good.
It seems it's working pretty well, at least with the test sample that you're obtaining from the original training sample. But I was wondering whether in the big sample, you could, I don't know, like add some extra layer of information. And I know you made an effort. You made an effort trying to get rid of spurious information, right? But it looks to me like the angular size of the object clearly have an impact on this.
Yeah. I think because the main idea of kind of redesign is because these visual inspections maybe were a bit complicated, like self-complicated, in order to maybe try to narrow down maybe a bit too much. So yeah, they will definitely keep it in mind for doing it again, kind of the resetting of the visual inspection. Yeah. Thank you.
Thanks.
Yeah. Thanks for the very nice talk. I have 2 questions related with the HSC data. Can you explain a little bit how the merger sample was defined? And secondly, it looks like when you apply the error as the main parameter to separate mergers and non-mergers, it doesn't work as well for HSC data. So do you think that could be related to an bad sky background subtraction from the SDSS pipeline, in the sense that doing things bad can help you to detect the mergers?
Yeah, that's a super good question. Probably. Yes, because so then this was in DR6, data release 6. For the data release 8, they made it different. So how they did it was, okay, maybe let's get some image that might help you show. So for what they did was they made boxes, right? And so boxes within the image, and they calculated the background in each box, and they were moving it.
Right?
Yes, but kind of to show. Sorry. Okay. Yeah. So how they did it in SDSS was like this. But in the data release 6, they didn't mask anything. Well, later on they did. It didn't. So when I applied the method or the neural network to file the data releases, it didn't got much worse, but still it did get worse. So I do think that like definitely that part of the reason why it appears is because of like not subtracting it correctly. Like they in fact need to correct it later on. And so yeah, which SSC I'm not entirely sure, because unless those background detections like they are not added back well or something, I'm not entirely sure what would be the effect, to be honest. Because if the background is not subtracted well in SDSS, I mean, here I am still trying to analyze them when the background is not subtracted, right? So I don't know, it's a bit tricky, but maybe, okay, maybe I understand now. So the reason why they appear is because the background is not well modeled. Okay, okay, I see.
And can you tell us a little bit about the HSC merger selection?
So this was from the HSC, so from the Galaxy Zoo H2 Not, that is the Galaxy Zoo Cosmic Dawn, that was the one of, I think, last year. So then we got the data from them. So from the votes from the program, I got the mergers from like high vote. It was similar to the previous data release because this data release of Galaxy Zoo still doesn't have paper. As far as I know, it was close to be released, but I think not yet. And then we got like a high vote. So the previous data release, I think, was the CALs, was votes from like about 0.7. So we selected those that were in our imprint that had these votes. And then the minor mergers were the ones with 0. But also one of the problems that we were having was that there were galaxies that were much more resolved than, for example, the one here. So there is some.
Because my point with the Galaxy Zoo merger is that it's not reliable in the sense that most of the times are closed pairs, and I found that myself when I trained a neural network to detect mergers with Galaxy Zoo in Sloan, and we found out that it detects closed pairs, but not mergers confirmed spectroscopically. So maybe that could be contaminating your merger sample a lot.
Yeah. Okay.
So if you have a spectroscopic information, to double check if the galaxy pairs are at the same redshift at least.
Okay. Yeah. Okay. Perfect. Okay. Yeah, because then I did look at them, but that's like at the beginning I made like a kind of raw selection, but then I end up with only 30 sources. So then I got a bit more general, which but probably would get more anyway. Yeah. Okay. Perfect. Thank you. Yeah, we definitely keep that in mind.
More questions?
Okay, thank you for the talk. It was very interesting. Also, here are the bisons. This is live. So everything else he said must be true as well. I found it really interesting, the idea that it was the errors in the end what worked best. But I don't know if I missed it looking for the bisons online, but it seemed to be like you started with the machine learning approach, and you got like 90 more than 90% in accuracy, and then it seems like you dropped it and you came back with a more traditional approach, like putting a line in a 2D in a 2D graph. And don't get me wrong, I do that. Like my interesting objects actually like very similar in the shape, not in the magnitude. But I was wondering if wouldn't that maybe tuning it a bit like you were tuning this other way of getting rid of the interlopers, etc. Wouldn't that be an interesting idea? I mean, I agree with Andres that trying other more parameters and doing I think a clustering, multidimensional clustering algorithm would work as well. But haven't you tried? Haven't you kept? Is it worse the first machine learning thing that you tried, or?
I for example, I didn't include it, but for this contamination thing, I did apply a CNN for finding the sources with the stars. Yeah, it was not dropped. It's kind of like this was the final result that we went for, but it for sure would be useful to keep it the CNN for finding at least the stars. And now I kind of reduced just to do dimensionality reduction. I think up to now I just didn't kind of either while planning or while doing things after one thing after the other, I just didn't point out or like, hey, it would be very good to have some model here. And also the other extension using machine learning, that is the CNN on the residuals, was then taken care by another colleague, another student. So maybe that's also why I separated. But yeah, I definitely would like to keep doing. And well, here now with Elena, I'm doing unsupervised learning with now with Mini Pass. So yeah, of course, I would like to keep doing that.
Someone has, I mean, this is like a compulsory question that you get asked if you give a talk here. Should we do this with JPass?
I don't know how the sky background error is done.
Sorry?
I don't know how the sky background error is obtained, so yeah. If not, we could, yeah.
Wrong, no.
I will definitely judge your pipeline regarding of when it is abstracted.
It's not yeah, I was surprised. Like nobody is asking about that.
We went to Granada for thesis. Or Julio Rodriguez, I think. Okay. Raul?
Yeah, so thanks a lot for the very nice talk. So related with the subtraction of the sky background with the HSC. So there was a very well-known problem about the sky over subtraction. I think it is described in IARA 2019, something like this. So my question is, are you using the data after this problem was solved, or this is previous to the?
It's the one after, yeah. It's the
So even with this corrected data, you see that the
no, like well, I mean on the pipeline. So on the paper, they are described right that it shows the two separations. So I think this is kind of showing that it is well done at it with the stars, because I haven't looked at it with bright galaxies, because I think that I sorry, I was gonna say. I think the main problem, right, was that they were having over subtraction in bright halos around bright sources.
yes.
So well, in this case is several bright sources, right? So it's more like the halos around the stars. So yeah, I haven't checked with like some big source in the field.
But the situation should be similar.
That's what I think. Yeah, that's what I think. So why my conclusion was that this one is similar was also related to that. Yeah. The main difference for them, for sure, was the addition of those two backgrounds. This is definitely not in the pipelines before. I'm not entirely sure how they do with the source detection part. I'm actually not sure.
This is the key step.
Oh,
So
sorry.
the detection of the sources is the key step.
Yeah.
If you are not able to detect completely all the sources.
Yeah. I think it was different because I think that also the three backgrounds were not added back either. Yeah. I think it's something like this. Yeah.
Okay.
Yeah, but I think that's the that's as far as I know. Thank you.
More questions? No? Let's thank again. And you're doing this.
Thank you.